Welcome to this explainer. Today, we're going to completely upgrade how you visualize the atom. If you've ever wondered how the universe is actually organized at the absolute most fundamental level, well, you are in the exact right place. We're going to explore the atom's true, three-dimensional architectural blueprint.
So where do electrons actually live? We so often picture them just orbiting a nucleus, like planets in a tiny little solar system. It's a classic image, right? But it's not exactly accurate. Today, we're zooming way down into the actual quantum architecture to see where these electron tenants truly reside. And trust me on this, their spatial arrangements are way more fascinating and structured than just simple circular orbits.
Okay, here's our agenda for mapping this out step by step. First, we'll meet the quantum shells. Then, we'll look at the subshell split. Third, we'll go inside the orbitals themselves. And finally, the rules of filling. Let's get into it.
Section 1. Meet the quantum shells, the main floors.
To really map this whole thing out, we have to look at the electronic configuration. Now, that might sound complicated, but it's really just the master manifest detailing the precise distribution of electrons across principal energy levels, or what we call quantum shells.
Notice how these principal quantum shells act literally just like floors in a building. You can see the nucleus sitting right there at the center, marked with a plus sign. Surrounding it are these concentric circles labeled n equals 1, n equals 2, and so on. That n right there, that is the principal quantum number. The lower the n number, the closer that shell is to the nucleus. And just like having to climb up higher in a massive building takes a lot more effort, the higher the n number, the further from the nucleus it is, and the higher the energy of that specific shell. Makes sense, right?
And, keeping with our building analogy, just like the upper floors of a giant skyscraper usually have way more square footage, these higher quantum shells can hold a much larger maximum number of electron tenants. Shell 1 is tiny. It holds only up to 2 electrons. But jump all the way up to shell 4 and wow, you have enough space for up to 32 electrons. That is a massive jump in capacity.
Okay, moving to Section 2. The subshell split, wings of the building.
So, a floor in a massive skyscraper isn't just one giant empty room, right? Let's zoom in and see how these principal shells are actually divided. This brilliantly illustrates this kind of Russian nesting doll concept we've got going on. Starting with the main shells at the bottom, if you pull out a section, it reveals they actually split into these smaller categories called subshells. And if you magnify those subshells even further, you find they contain the final specific locations, the orbitals. So, what exactly are these subshells? Well, think of them as different wings, or maybe different apartment layouts on each floor. Now, apart from the very first shell, all the principal shells split into these subshells, and they're labeled with the letters S, P, D, and F. Generally speaking, the energy of these wings increases in that exact order. So S has the lowest energy, then P, then D, and finally F. Oh, and a quick side note, you really only start seeing electrons in the F subshell when you're dealing with the heavy hitters, elements with over 57 electrons.
Tracing this whole thing out here, you can clearly see how the principal quantum shells on the left branch out into these distinct subshell energy levels on the right. Notice how n equals 1 is just a really simple 1s level. But look up at n equals 3 and n equals 4. Things start to get a bit crowded up there, don't they? The energy levels of the different wings actually start to overlap. Keep that in the back of your mind, because that overlap is going to be incredibly important in just a few minutes.
Which brings us to Section 3. Inside the orbitals, the actual rooms.
Okay, so we've seen the floors, we've explored the wings. Now let's zoom in one last time to the absolute micro level, the actual physical spaces where these electrons live. The crucial takeaway here is the definition of an atomic orbital, because no matter how massive the principal shell is or how complex the subshell wing is, the actual atomic orbital itself is an exclusive, highly specific region of space. And the absolute golden rule of this quantum real estate, this room holds a strict maximum of 2 electrons. Never 3, never 4, just 2.
So what do these rooms actually look like? While comparing these spaces, look over on the left. The s orbitals are perfectly spherical. They're super simple, and they just grow larger as you move to those higher floors. So a 3s orbital is going to be much larger than a 1s orbital. Meanwhile, on the right, check out the p orbitals. They're shaped kind of like dumbbells or maybe hourglasses, and because of this unique shape, they point in 3 totally different directions along a 3D grid, specifically the x, y, and z axes. That 3D orientation right there is exactly why a p subshell has 3 separate orbitals packed within it.
Now, I know that is a lot of terminology to throw at you, so here's a really helpful cheat sheet summarizing our entire quantum architecture math. You can clearly trace how the principal shell number dictates literally everything else. Just take shell 2, for example.
It has S and P subshells. The S has 1 room, the P has 3 rooms, right? That's 4 rooms total. Multiply that by 2 electrons per room, and bam, you get exactly 8 total electrons. The math scales up perfectly through this entire table.
All right, Section 4, the rules of filling. Who moves in first?
Which brings us to the final piece of our puzzle. If you're an electron looking to move into this building, what are the rules of tenancy? How exactly does the building fill up? Well, to understand this, we have to talk about the ground state. You see, nature is fundamentally lazy, but in the best way possible. Electrons always seek the ground state, which is simply the most stable arrangement with the absolute lowest amount of energy. To achieve this perfect stability, electrons will always move into the lowest available energy subshells first.
Now remember earlier when I said things get kind of crowded and overlap? Well, here is a really surprising architectural quirk in our atomic building. Because the energy levels get so incredibly tightly packed as you move further from the nucleus, the 4s room is actually slightly lower in energy than the 3d room. I know, it's wild. Even though 3d is technically on the 3rd floor and 4s is on the 4th floor, the 4s room is just easier to live in. So our electron tenants actually move into 4s before they even touch 3d.
And because of these weird overlaps, simply counting 1, 2, 3, 4 just doesn't work. Instead, this diagonal mapping provides the absolute ultimate guide. By writing out the subshells in rows and following those red arrows, you just read from the tail to the tip, and that shows you the exact perfect sequence of filling, from the lowest energy straight on up.
Let's quickly walk through that sequence together just to really cement this. We start right down at the bottom, 1s. Then we move up to floor 2, filling 2s and then 2p. Then up to floor 3, filling 3s, then 3p. And then, boom, we hit that critical skip. Following the diagonal arrow, we hit the 4s room before looping back around to the 3d room. Honestly, if you can just remember that one major detour, you can successfully map out almost any element.
And that brings us to the end of our quantum architectural tour. Now that you really understand the true invisible structure of the atom, the shells, the subshells, the specific orbitals, and exactly how they all fill up, it leaves us with an incredibly exciting question to ponder. Knowing this intricate quantum architecture, how does the arrangement of these specific outermost rooms dictate exactly how elements interact, share electrons, and bond together to create absolutely everything in the universe around us? Think about that quantum architecture the next time you look at the world. Thanks so much for joining me on this explainer.